but they're not there.
Anywho, yes, welcome to CS161 lecture number 2. We're going to be talking a little bit about x86 assembly and the call stack, and we're going to do a little bit of 61C review as well. So last time we talked a bit about security principles. We talked about what is security as a whole. And these security principles, we're not going to talk about them explicitly too much again, but I just hope that you're keeping them in mind as we move through the next 8 weeks of this course. Just as a side note, if you have any questions, always feel free to put them in the chat, or you can also raise your hand and ask them aloud if you feel comfortable. I checked the recording last time, and I believe it's only my face that actually appears in the recording. So if you're comfortable, also feel free to turn on your camera. It just lets you see everyone else. But yeah, it helps me as well because I get to see everyone. And here, yes, today we're going to spend the first half talking about 61C content. So it's going to talk about number representation. It's going to talk about how we write programs and then turn them into code that the computer can understand. And then we're going to talk about how the computer organizes different segments of memory in order to ultimately run the program. After that, we're going to talk about x86 assembly. So x86 is the assembly language that we're going to use in this course. And then we're going to talk about specifically the calling convention. There's a question about project 1. We're hoping to release project 1 by the end of today. So keep an eye out for that. All right, number representation. So remember that in the world of computers, all data has to be represented as bits and bytes. So in a computer, we have wires, and those wires can really only have a high signal or a low signal. So those are our ones and zeros, respectively. We call these a bit. So this bit is a binary digit. It's either a 0 or a 1. When we group bits together, we have names for larger collections of bits. So 4 bits we usually call a nibble. This is not a very common term, but you will see it around. And 8 bits is called a byte. This is probably a term that you've seen before. So for example, this sequence of bits here, we've just started with 0B to denote that this is binary. We have 16 bits here. So this is 16 bits. You can also call it 4 nibbles, or you can call it 2 bytes. When we're writing out groups of bits, oftentimes we're going to be working with 32-bit numbers. 32 bits is just a lot of bits to write out. So I don't really want to be writing 32 characters every time I want to write out a number. So we have a hexadecimal notation. Each hexadecimal digit, or maybe it's hexadigit, I'm not actually sure, will represent 4 bytes. So because 4 bits can represent 16 different values. So there are 16 different hexadecimal digits. That's why it's called hexadecimal. This is the table to convert between the two. Hopefully you're a bit familiar with this. It just makes life easier to be able to look at, say, 1101 and know that it's already the hexadecimal digit D. But if not, this table is here for you as a reference, and you can always look it up online. When we're writing things out, this is 1 byte. Remember, there are 8 bits here. We're going to take the first 4 bits, compress them down into the hexadecimal digit C, and we're going to take the second 4 bits and compress them down into the hexadecimal digit 6. Remember, these are the same value. It's just a more compressed, more compact way of writing things out. And yes, this is the prefix that we use. For hexadecimal, we'll use 0x, just so that you know that this is hexadecimal, and for binary, we usually use 0b. The 0 prefix, I'm not actually sure. I'm not sure if Perrin has an answer for that. It's just sort of the convention that we've come up with.
Yeah, I don't know off the top of my head, but I'm sure if you looked it up on Google,
Yeah,
you can
I'm not sure. Good question.
find something useful. Yeah.
All right. When we're running C programs, we start with C code. C code is what we call a high-level language. It's easy for us humans to understand. We can write while loops, we can write functions, we can write if statements. But this code isn't really something that a computer can understand. This code is really just a text file if you actually look at the bytes that make up C code. So what we want to do is we want to convert it into a language that computers can understand. Now, the intermediate step that we have in between is assembly code. This assembly code is still a text file. So when you're writing assembly, you're still writing literal characters like the letter A or the letter S over here. But it's code that can be easily translated into bits and bytes that a machine can understand. So when we convert this assembly code into the raw bits and bytes that make up each instruction here, this sequence of bytes is what the CPU can actually read from memory, and it's what the CPU can actually execute. The process for turning C code, or any code really, into assembly code is known as compiling. And the process of turning assembly code into the raw bits and bytes that the CPU understands is known as assembly. So that's the first two steps of the call acronym that we have here. Call stands for compiler, assembler, linker, loader. It's just the process by which we eventually execute programs. So after the compiler and after the assembler, we have the linker. What the linker does is it links our code, the code that we've written, with other code in other libraries. So if you think of, say, the malloc function, we use malloc to allocate memory. You never had to go and write a malloc function. Someone else has already written malloc for us, and we're just using their function call. What we do when we want to execute the program is we have a little slot in our executable that says, okay, I need to execute a malloc function. And then the linker's job is to go and actually link that little symbol against the real malloc code that is somewhere in some shared library on your computer. So the linker links everything together so that the CPU just has to deal with a really long string of instructions. You don't have to use this for 161. This is just part of the call sequence. Finally, we have the loader. Normally, the executable is going to be stored as a file on your hard drive or on your solid state drive, maybe. But the CPU needs to be able to load instructions from memory. So the loader's job is to read this file. It will set up all of the memory in your computer, and then it will direct the CPU to begin executing instructions wherever the loader loaded your piece of code. Okay, so now that we're talking about memory, we're going to talk about a couple of different parts of memory. At runtime, what the loader is going to do is it's going to ask your operating system to give it just a big blob of memory, because it needs that memory to load the program, and it needs that memory to store variables and edit anything else that you want to work with. On a 32-bit system, this memory is going to have 32-bit addresses. So nowadays, more commonly, we'll see 64-bit systems, which has 64-bit addresses. But for simplicity and for certain other reasons that we'll get into next time, we're just going to work with 32-bit systems. That and the addresses are shorter to write out. Otherwise, you have to write out 16 hexadecimal digits, which is just too much. My transitions are a little slow today, sorry. Each address is going to refer to a single byte. So because we have 32-bit in our addresses, we have 2 to the 32 possible addresses. That means we can address 2 to the 32 bytes of memory. This is about 4 gigabytes. It's not too important for this class, but it's generally smaller than most modern computers today, which is why we generally move to 64-bit architectures. The abstraction that memory usually appears as to the computer is basically just a really long contiguous series of bytes. So at the very left here, we've got the address 0000000. This is what we call a null pointer. And at the very top here, we've got FFFFFFF. And it's really just a really long sequence of bytes. And you can write anywhere to memory, and you can read anywhere from memory, usually. When we're dealing with memory, when we're trying to write memory out ourselves, so this abstraction is not really useful for us, or this layout is not very useful for us because it's just too long and it's really clunky. So in this class, we're going to write the stack out like this. This is what we're going to call, not the stack, just any piece of memory. Lower addresses are going to go at the bottom. So here's our 00000 again. And at the high addresses will be at the top. So FFFFFF. Usually this will be 4 bytes across, just because 4 bytes is 32 bits. So it's really convenient for us to just write values like this. And yeah. But remember that the CPU still really just sees a really long contiguous array of bytes, and the CPU can write anywhere, to and from anywhere. All right. Questions on any of that so far? right. So we're going to dive a little bit more into x86 specific stuff now. In x86, we have 4 main segments of memory that we need to worry about. The first is the code. So remember, the loader is going to load your CPU instructions somewhere into memory so that the CPU can execute them. The place that the loader loads this code to is called the code segment. Sometimes it's called the text segment. It doesn't really matter. The data segment is for static variables. So sometimes when we're writing code, we already know, oh, when the program runs, I already know that I need 2 integers somewhere in memory, for example. So this is static variables, and they're allocated when the program is started before the CPU has even started executing instructions. After that, we have the heap. So the heap is where we store dynamically allocated memory. This is where you get memory. This is where memory comes from when you malloc something, and this is where memory is freed when you free something. The key here is that if you don't free it, the memory will just stay allocated forever. So this is where most of your memory leaks will come from. And when you allocate a large amount of memory, if you just keep allocating memory, the heap is going to grow upwards. So the heap, it starts down here, and eventually the malloc function, if it needs more, it will continue to grow the heap upwards towards higher memory addresses. This is in contrast to the stack. The stack is used to store local variables. So when you declare something within a function, that's a local variable. It contains the stack frames. So the stack frames are what's used to store the execution state of different functions. When you call a function, what you need to do is your CPU needs to jump to a different location in memory and start executing instructions there. So what we want is to save the execution state before we jump there so that eventually we can return. As you call more and more functions, it creates more and more stack frames. So when we have more and more stack frames, the stack is going to grow downwards. So there's a space between the heap and the stack. And as the heap grows, it's going to go upwards towards the stack. And as the stack grows, it's going to grow downwards towards the heap. Okay, in this class, we're going to deal with unoptimized code. Oftentimes in the real world, you'll see optimized code, which is really difficult to read and uses really bizarre CPU instructions. In this class, we're dealing with unoptimized code. So this means that local variables are always going to be stored on the stack. This is in contrast to RISC-V, which has plenty of registers. RISC-V has 32 registers, so most of the local variables can usually be stored in the registers rather than going to and from memory every time I want to do an operation. In the stack, individual variables are going to be stored with the first variable at the lowest memory address. And you'll see an example of this in a moment. By contrast, members of structs, as well as global variables, the first member or the first variable is going to be stored at the lowest memory address. So it's a little bit reversed between stack variables and structs and global variables. And hopefully this will be clear in the next example that I have. So here we have a struct definition. We have f1, f2, f3. And then in this function here, we have int a, int c, as well as a struct foo b. Keep in mind that these all have different sizes. So how would you fill this stack diagram in? Again, lower addresses are at the bottom and higher addresses are at the top. So what would go here, what would go here, 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 and here? And really quickly, I'll give you 15 seconds to type an answer into the chat. A, BF3, BF2, BF1, and C. That is correct. I guess I didn't specify which direction we want to go in, but yes, that's exactly correct, assuming that you're going from the top down. Because A is our first local variable, it's going to go at the highest address. So A goes at this highest address up here, and likewise C is the last local variable, so it goes at the lowest address down here. B goes in the middle because B is in the middle. Within the struct, the things are reversed. So if we looked at the struct definition, This F1 is the first declaration, so it's going to go at the lowest address within that struct. And we have 2 of them because F1 is 8 bytes. Then we have F2, then we have F3 because F3 is the last one, so it goes at the highest memory address because it's within a struct. Any questions on why this is true? Does all make sense? Okay, awesome. Okay, now we're going to dive into the real meat of x86. So the first question that you always have to ask yourself when you're working with x86 is, why are we using x86? The simplest reason is it's the most commonly used architecture in consumer computers. So if you're using something that's not a phone, that's not a tablet, or a recent MacBook, or Mac Mini, or actually I think they have quite a few Macs with the ARM chips now, you're almost definitely using an x86 computer. I'm using an x86 computer for this. And because this is a computer security class, and we want you to be familiar with how these attacks work in the real world, we want to use the most commonly used architecture, because this is what's used in servers, and this is what's used in computers that are hacked daily. Other than that, x86 is kind of a piece of hot garbage. It's a really old architecture. So it was designed back in the 1970s, I believe. And this means that it has a lot of legacy and it has a lot of backwards compatibility that it needs to maintain. And it means that the language today is really difficult to understand and it's really bloated. We are not going to expect you to know x86 like the back of your hand. All you really need to be able to do is be able to get through project 1 and be able to look at x86 code and have some idea of, okay, I know what this function is doing. Just a quick note, I'm going to make a lot of references to RISC-V. I know this is a summer semester, so a lot of you probably haven't taken 61C. 61C uses RISC-V as its assembly language, which is why I make these comparisons, because I'm assuming enough of you have taken it that these comparisons will be helpful. But if you don't understand the comparisons, that's completely okay. You don't need to understand the comparisons to actually understand x86. They're just there for the people that they would help. All right, so just a brief introduction to x86. It's something called a CISC architecture. So this is the opposite of a RISC architecture. A CISC architecture is a complex instruction set. So this means it has a lot of instructions and they do a lot of different things. They have instructions to encrypt things. They have instructions to perform complex mathematical functions. And this means that the instruction set manual for x86 is over 5,000 pages long, which is not even a number that I can comprehend. This is like, compare this to RISC-V, which you learned in 61C, which has a manual that is, I think, barely 200 pages long. It's very hard to understand and implement. We're not going to be teaching the full instruction set, obviously. Again, we're just teaching enough for you to be able to do project 1. It was launched in 1978 with the Intel 8086, and it was then that it sort of took over all of computing. And notice, again, this was over 40 years ago, which is why the instruction set today is very bloated, very, very bloated. There's also a 64-bit variant called x86-64 in 1999. We won't worry too much about this. All right. So first thing about x86 is that it is little endian. So remember, usually we're going to be working with either 32-bit integers or 64-bit integers. The fact that it's little endian means that the least significant byte goes at the lowest memory address. This is the same as RISC-V. Second thing is that operations can use data either in registers or in memory. So in RISC-V, you could only use data that's in registers. So if you wanted to do something with data, you would have to use a load instruction to load it into a register, and then say an add instruction to operate on that data. In x86, you can actually do that all in one instruction. It automatically accesses memory and then does some operation on it and maybe even stores it back to memory. So it's a lot more complex in that way, which is why it's a complex instruction set architecture. And finally, it has variable length instructions. So this means that when the assembler turns the instructions into machine code, it's not always going to be 4 bytes like in RISC-V. some instructions are 1 byte long and some instructions are 16 bytes long. I thought they could go higher than that, but I'm just going to go by what I've written on the slides. And yeah, contrast with RISC-V, which only has 4 byte instructions. The x86 architecture. So remember, registers are not on this diagram. Registers are pieces of memory within the CPU itself that the CPU has really fast access to and is able to perform computations on without having to go onto memory. So this is a trick question. They're not anywhere on this CPU or on this diagram. In x86, there are only 8 main general purpose registers. So you will see registers called EAX, EBX, ECX, EDX, ESI, and EDI. These all stand for something. You don't have to worry about what they stand for. You'll just see these in assembly code. The 7th register that we have is the ESP. So this is the stack pointer. This points to the bottom of the stack. If you remember, the stack grows downwards. And this is similar to the stack pointer in RISC-V. The final register that we have is the EBP, the base pointer. So most people haven't used the frame pointer in RISC-V, but essentially what this is it points to the top of the current stack frame, just so that we know where we are in the stack. We'll see a more clear example of this later, but just keep in mind that this is similar to the frame pointer in RISC-V if you've used it, and if you haven't, don't worry about it. The EIP is another register in x86, and this points to the current or the next instruction that we're going to execute. So this is similar to the program counter in RISC-V. It's just that in x86, it's more of a real architectural register rather than a separate thing, separate from the register file in RISC-V. There are a lot of other registers. I think someone pointed in chat earlier that there are vector registers that are complicated. You might see them in project 1, you might not. You don't have to worry about them. In x86-64, if you ever wanted to run GDB on your own computer, which is probably a 64-bit computer, you'll see the R prefix instead of the E prefix. So instead of EAX, you'll see RAX. Instead of EBX, you'll see RBX, and so on and so forth. The stack pointers ESP is RSP instead of ESP. Yes, we can skip past that. All right, x86 assembly. We're going to use something called AT&T syntax. The alternative to this is Intel syntax, which you might have come across if you've written x86 before. We use AT&T syntax mainly just because it's the one used by GDB, and it's the one that you'll see in Project 1 because you'll be using GDB in Project 1. If we want to reference a register in x86 assembly, what we're going to do is precede it with a percent sign. So, for example, if I wanted, oh, I did it again. Okay. If I wanted to reference the EAX register, I would do %EAX. If I wanted to reference the ESP register, I would reference %ESP, and so on and so forth. If I wanted an immediate, so remember an immediate is a literal value that's encoded into the instruction itself. If I wanted to represent a literal value, what I do is I use a $sign. So for example, if I wanted to represent the literal value 1, I could do $1. If I wanted to do 161, then I'll do $161, and I can also do it in hex. So I believe GDB will show most values in hex. If I do $0x4, this is 4 in hex. Which is also 4 in decimal, but that's beside the point. Oh, okay, I did it again. I need to, I believe, only click on the speaker view instead of trying to advance the slides on the actual screen. Sorry about that. And finally, we can do memory references in x86. So remember, instructions can directly access memory without an explicit load. So we use parentheses to denote, okay, we're going to take this value in the ESP. We're going to access the value at that address stored within ESP. And in this case, we're saying we're going 8 bytes above it. So this is similar to the load store syntax in RISC-V if you've used it. If you don't see an explicit offset, then I'm sorry, I forgot to move the dogs out of my room. Then there will be an implicit 0. So this is the value at the address stored in EAX without any offset. All right. Any questions on any of this so far? Can you put a negative number for the offset? Yes. Yes, you can. I don't remember the range for the immediates off the top of my head. It's not something that you need to worry about. Any other questions? All right. In x86 assembly, instructions are going to have an opcode. So this is what the CPU is actually going to do. And it's going to have 0 or more operands. So most arithmetic instructions are going to be either register-register. So they operate between 2 registers on the CPU. It can be register immediate. So it's between a register and a literal value. It could be register memory. So it can operate between a register and a reference stored in memory itself. Or it can be memory immediate. So again, between memory and between a literal value. The thing to remember here is you can't do memory instructions. The assembler will just sort of spit out an error if you try to do this. A lot of instructions are going to use implicit registers. So this is one of the weird things that's hard to wrap your mind around sometimes in x86. Whereas in RISC-V, you always had to specify the registers, and the only registers you specified are the only ones that would be used. In x86, some instructions will use implicit registers. So for example, in x86, we have a push instruction. The push instruction will push something onto the stack. So in order to push something on the stack, what we need to do is we need to move the stack pointer down so we have more space on the stack, and then we need to store a value onto the stack. So even though we're not specifying the ESP register in the push instruction itself, the push instruction will still change the ESP. The ESP is implicitly referenced by the push instruction. Finally, this is something that you'll see in GDB. Most instructions have a suffix that will denote the size of their operands. So in 32-bit architectures, usually you'll see the L suffix. You might also see B, W, or Q, depending on if you're using 8, 16, or 64-bit operands. But again, usually you'll see 32-bit operands in most circumstances. Also most arithmetic instructions are going to use the destination operand as the source operand. So in RISC-V, we had an explicit destination, an explicit source 1, and an explicit source 2. But in x86, we only have 2 sources, and the last operand is also the destination. So the last operand gets clobbered as both the source and the destination. I'll go over into more detail on this example slide. Okay, for example, here is an add instruction. So this is the add. It has the suffix L, so it's operating on 32-bit numbers. The source in this case is going to be an immediate. So this is the immediate representing the value 8. And this is the destination. So we're referencing the value in EBX. The pseudocode for this is set EBX equal to the value in EBX plus 8. So remember, both of these are source operands, and the second one is also the destination. So in this case, we see EBX referenced twice. And what this will do is just increment the value in EBX by 8. Notice, again, the destination comes last. In RISC-V, the destination came first. So this might be something that you'll have to get used to if you took 61C, but in x86, in AT&T syntax, the destination comes at the end. The add instruction, yes, the add instruction only has 2 operands, and the destination is an input. We talked about this already. All right, I have another example here. We have the XOR instruction. Again, this is operating on 32-bit numbers. In this case, we are referencing 4 bytes above the address stored in ESI. So ESI contains an address. We're going 4 bytes above that, and that's our first operand. So we're actually going to access memory 4 bytes above the pointer stored in ESI, and we're going to XOR that value from memory with EAX. So the source code here is EAX equals EAX XORed with the result of dereferencing ESI plus 4. Yes, note this is a memory reference. This is not like most things that you have seen in RISC-V. All right, that is it with x86 assembly. Are there any questions? All right, I'm going to step away for 5 seconds to close that door. All right. Okay, now we get into calling convention. So this is the, actually, I'll just explain that on the next slide. So remember that the calling convention is an understood way for functions to call other functions, and it will have a guarantee for what state the processor will return in. So you can imagine if I called a function and like when it came back to me, all of the registers were changed and all of memory is now different, then I would never be able to do anything after I called that function. So what I want is a guarantee that, oh, my registers are going to stay the same, and my values in memory are also going to stay the same. It's a guarantee. There are 3 main parts to a calling convention. There's how to pass arguments. So I have to know, how do I tell the function that I'm calling what arguments that I'm actually giving it? And then the callee will know where to look for the arguments in the calling convention. I also have to know, how do I receive return values? The callee is going to pass a return value back to me, and I have to know how to get that return value. Finally, I have to know which registers are caller saved and callee saved. So callee saved means that the called function can't change the value of the register when it returns. It can change it in between, but when it returns from the function, it has to be its original value. By contrast, caller saved means that the called function is allowed to overwrite the register, and it's up to the caller to save the register if it wants to keep that value. We're going to use what's called the C declaration syntax calling convention. This is the most widely used one. You don't have to remember this name. It's just what it's called. All right, so first, arguments. Arguments are passed on the stack. Arguments are going to be pushed onto the stack in reverse order. So if I'm calling the func function and I'm passing it 3 values, val1, val2, val3, I'm going to push val3, then push val2, then push val1. Remember, the stack goes downwards. So when I push val3 first, it's going to end up at the highest memory address. And then I'll push val2 below that, and I'll push val1 below that. Again, you'll see an example of this when we walk through the full calling convention. Oh, I did. Yeah, contrast with RISC-V where the arguments are passed in registers A0 through A7. The return values are passed in the EAX register. So this is similar to RISC-V where the return values are passed in A0 and A1. When I call a function, I expect that the return value will come back to me set in EAX. Finally, in x86, EAX, ECX, and EDX, those are all caller saved. So those are basically temporaries that the call E is allowed to change at any time. And everything else is a caller saved register. All right. Speaking of saved registers, the idea is when I call a function, I want the registers to come back to me the same way that I left them. So I don't have to worry about reinitializing all of them and saving everything on the stack just to restore them. I feel like this slide was duplicated from somewhere. All right, we've talked about most of this, so I'm going to skip past this slide. Yes. All right. So the first instruction that we have in our x86 calling convention is the call instruction. My call instruction is going to do 2 things. First, it's going to push the address of the next instruction onto the stack. First thing to remember is the next instruction is not necessarily EIP plus 4. It's just the length of, it's EIP plus the length of the instruction. Again, not too important, just keep that in mind. First, we need to decrement the stack pointer. So ESP equals ESP minus 4 because we need to allocate space for that pointer on the stack. And then we're going to store that push value to memory. So the next EIP is going to get stored to the address that the ESP now contains. Second, the call instruction is going to set the EIP to the address of the called function. So we want to jump to the code that we're calling. So now we're saying just EIP equals the address of the function. So call does two things. One of those things is also two things. So it does like, I guess, three things. It's not too important. This is just what the instruction does. Technically, you have like three different types of calls. This is not really important. The stored instruction pointer on the stack is called the return instruction pointer. It's the instruction pointer that we're going to use to return from the called function. And this is abbreviated as the RIP. You're going to see this come up a lot when we write out our stack diagrams, and you're going to see this come up a lot when we begin to exploit this calling convention. Next lecture. To return from a function, we have the ret instruction. So this is going to pop a value off the bottom of the stack, and at that point, we're expecting it to be the RIP and stores it into the EIP. So this is really two things. One, it's going to set the value of the EIP to whatever is at the bottom of the stack, because we're expecting that to be the RIP. So we're returning to our original flow of execution. Then we're going to increment the stack pointer. So now that we're done with that value, we can move the ESP back up. Does x86 also have delayed branch instructions where it does not. I believe you're referring to a branch delay slot. It does not. It's not too important. I believe MIPS does. So if that's what you're thinking about, x86 does not have that. All right. This is a really simple x86 function. We have our main function over here, and all that main does is it calls do nothing. Do nothing actually does nothing. I guess we've made it do something here, but it's not too important. When we call do nothing, the flow of execution jumps to this XOR. EAX gets XORed with EBX, and then we return. So the question here is, does do nothing follow calling convention? I guess I have to say yes or no in the chat. Do you think that do nothing follows calling convention in this case? I have a no. All right, yes. All right. In fact, yes, this does follow calling convention. Andrew, I'll get to your question in a moment. Remember that EAX is a callee saved register. So even though do nothing ostensibly doesn't actually do anything, when main calls do nothing, it can't make any assumptions about EAX, ECX, or EDX, because those are all caller saved registers. So even though it's not saving the value of EAX, it doesn't have to, because do nothing is allowed to change EAX, ECX, and EDX however it wants. And when we're reading EBX, it doesn't change its value. Do nothing is just a function that I've named in the C code. This is a label here that we can jump to when we are calling the function. It's not really an instruction. It's just the name of the function. All right. However, notice that if we're stuck using only EAX, ECX, and EDX, we don't have much functionality. So we need to start saving registers when we have when we want to have more complicated behavior. So the most commonly saved register is the EBP, the base pointer, which I mentioned earlier. x86 uses the EBP to refer to local variables and arguments relative to the top of the stack frame. In theory, if you've worked with RISC-V, you can refer to local variables relative to the ESP. So if I know that, oh, variable A is always 8 bytes above the stack pointer, then you could do that in theory, but this does cause issues sometimes if you move the ESP depending on some value that's not known at compile time, because then I don't know it's 8 bytes above the stack pointer. So instead, what I say it's 16 bytes below the top of the stack frame. Again, we'll see this all put together finally when we get to the calling convention example. We also save this so that our function can have its own local variables, because we want local variables in our functions. So we're going to need to save the EBP so that we can have a new EBP of our own. The EBP is always going to be saved first. And when we save it on the stack, it's known as the saved frame pointer, SFP. So normally when we're working with stack diagrams, you'll see SFP and RIP on the stack diagrams. For this class, you can usually assume that only the EBP is saved and there are no additional saved registers. I say usually because you may or may not come across a time where more than the EBP is saved in project 1. So you'll definitely want to check your addresses when you start working on that project. All right, here is an example of a more complicated function. Obviously, this is not optimized code, but we're just working with this for the sake of simplicity, or for the sake of ease of reading, funnily enough. This function has a local variable added, which just takes a+1 and it returns added. So what we have is we have a function prologue that will save all the registers that we need to save and set everything up for our own function. We have the function body in the middle, and then we have our function epilogue, which restores the state that the caller is expecting. So up here, what we're going to do is we save the EBP on the stack. We do that by pushing it onto the stack. Remember this push instruction. And then we're going to move the ESP down to the EBP. So we're done with, or we're going to ignore the stack frame above us, and we're going to set up our new stack frame by moving the EBP down. And then we're going to move the ESP down by 4 to allocate space for our local variable here into added. I'll have a stack diagram set up for a more complicated example. Likewise, down here, we will move the ESP back up to the EBP. So remember, this ESP is the second operand, so the second operand is what is moving around. And then we pop that value off the stack. So we restore the SFP back into the EBP, and then we return. Again, this will be more clear in the next example. And in retrospect, I think I will edit these slides to have a stack diagram earlier because it doesn't make much sense with me just talking about it. So sorry about that, but I hope it will make more sense in the next example with the stack diagram. Just something to keep in note, sometimes this function epilogue will be replaced by this 2-byte sequence. So before, where this is moving, popping, and then returning, we can also just have this leave instruction. So it's not too important that you remember this, but this is something that you will see in project 1. This leave instruction really just encompasses moving the ESP back up to the top of the stack frame to deallocate the stack and popping off the value at the bottom of the new stack where the SFP is stored and saving that back into the EBP. So this is just something that you'll see in project 1. All right, let's do a full example of how to call a function. So here I have my caller, and here I have my callee, which is do thing. I have a local variable f, a local variable b, which has values 1 and 2 respectively. And then I'll have a local variable foobar, which calls function with f and b. Oh, that's a typo. This is supposed to be do thing. I must have changed the function name at some point. Sorry about that. Okay, so we're going to enter the function right here. So just assume that caller has been called by somewhere else, or somehow we jumped into this piece of code. So when we jumped to caller, that call instruction pushed the RIP onto the stack diagram. After that, we're going to execute this first push instruction. So remember, the push instruction takes this value, the value of the EBP, and stores it onto the stack while also moving the ESP downwards. So this push instruction moved the ESP down, and then it took the value of this EBP and stored it in the stack here. So you'll see that these are pointing to the same thing because these have the same value. They're the same pointer. Next, oh yes, instructions that were just executed are in red. So we just executed this, and the EIP points to the address of the next instruction. All right. After this, what we're going to do is we're going to take the value in ESP and move that into the EBP. So the value of ESP is pointing here. So now the value of EBP is now pointing here, which is why the EBP moves downwards. So we're going to just ignore the upper stack frame now. We're going to open our new stack frame, and for that we need the EBP to be where we want it, which is why we've moved it. Finally, as part of the prologue, we're going to move the ESP downwards by 12. This is so that we have space on the stack to allocate our local variables. Remember that f was declared first, so it goes at the highest memory address here. So we have f at the I guess, highest 4 bytes, B in the middle, and then foobar at the lowest 4 bytes. These are currently uninitialized because we haven't written anything to those values, so they're uninitialized values in memory. In the function, we set f equals 1 and b equals 2. So we're just going to do that in this assembly language here. Move the value 1 into 4 bytes below the EBP. So we're referencing f, which is 4 bytes below here. And then move the value 2 into 8 bytes below the EBP. So move the value 2 into b here. Now these are initialized. We know what their values are. Push. Yes, okay. So next what we need to do is we need to actually call this function. So in calling convention, arguments are passed to the callee by pushing them onto the stack. So even though we have the values up here already, what we need to do is we need to push the value that is 8 bytes below here. So b is the last argument, it gets pushed on first. And then a, which is just the name of the parameter, is the first argument, so it gets pushed on last, which means it goes at the bottom memory address. So those are these 2 push instructions here. And finally, we execute this call instruction. So this call instruction means that the EIP is going to jump to do thing. And at the same time, it's going to move the ESP down so that we have space to store our RIP. And it's going to actually store the RIP. So the RIP, again, it's the return instruction pointer. It points to the next instruction in memory that we're going to execute once we return. So the next instruction is this add L, which is why we are sort of pointing all the way over here. All right, now the EIP is up here. We're going to start executing the instructions here. So notice we have the exact same function prolog. In this case, remember that I'll go all the way back. Remember that this added function has its, or not this one. What am I looking at? Okay, I guess we have a local variable here. I must have misplaced that. Sorry about that. But we're going to start executing the function prolog of do thing. So again, we push the value of the EBP. So now the SFP is pointing to where the EBP currently is. And then we're moving the EBP downward. So now we're ignoring this stack frame, and we're going to start dealing with memory down here. And I guess in this function, we have a local var. There it is, local var for do thing. We're just assuming it only needs 4 bytes of memory for one local variable or something. So that's where that's going to be allocated. Somehow in this function body, we know that EAX is going to be set to 42, because EAX is how we return values to the callee, to the caller. So once that's done, we're going to start returning from these functions. The first step is to move the value of the EBP into the ESP. So what this does is the ESP moves up by 4 bytes to deallocate this local variable. Next, we're going to pop the EBP. So this tends to be the most confusing functions for some students to understand, the most confusing instruction for some students to understand. Popping means we remove an item from the stack and we store it into the destination register. So what we're going to do is we're going to remove this SFP from the stack and store it into the destination, which is EBP. So SFP is pointing up here, which is why the EBP moves back up to where this is. And because we removed an item from the stack, we need to move the ESP upwards by 4, because now there's one less item on the stack. So we're shrinking the stack and it's going back up. Finally, we're going to return. So remember, this return instruction looks at the bottom of the stack and is going to set the EIP back there. So because the RIP is pointing to the next instruction that we want to return after having called the function, this retch instruction will set EIP back to where we wanted to go. ESP moves up by 4 again because we removed an item from the stack. We removed the RIP, and now our EIP is back where we want it. Notice that before and after we called this add1 function, I just realized I have 3 different names for this function. Sorry about that. This should be do thing. I'll make sure I have it fixed in the slides afterwards. Before and after we called this function, EBP and ESP are in exactly the same position. So that's what we want because these are callee saved registers. We want them to be restored when we return from the function, so we don't have to worry about, oh, did the function I called change their values? Finally, because we manually push the arguments on the stack, we need to manually deallocate them. So we're going to add 8 to the ESP just to get rid of these off the stack. Finally, what we did is we're returning the return value of this function. Or we're using the return value of this function. So we know that the return value was returned in EAX, and we're going to store that into foobar, which we know is 12 bytes below the EBP. So we move the value from EAX into 12 bytes below the EBP. After this, we have our same function prologue, function epilogue. So what we do is we move the ESP back up to the EBP. That's this move instruction here. Then we pop off the bottom of the stack. So at the bottom of the stack is the SFPF caller. We store that into the EBP, so the EBP moves back up, and the ESP moves up by 4, again, because we removed an item from the stack. Finally, we execute the return instruction. So when we entered this caller function, the call instruction would have pushed the RIP back on, and now that we're returning to wherever it went. So I don't know where the EIP went because we don't know who the caller was, but that is the end of this function execution. We've gone through this entire function. We went through this function along the way, and then we returned back to our caller. All right, that actually brings us to the end of the slides for today. We ended half an hour early, so I guess if you wanted to leave early, feel free. But are there any questions from anyone before we go? I know this was a huge information dump. This lecture didn't used to exist, so it had to be like compressed in from other review sessions in the past. But are there any questions on how this works? I can also explain things again if people are just sort of generally confused. Can we go over the function? Do you mean the instruction suffixes, or do you mean the function epilogue? The green part, yes. Sure. So remember that we want to restore the state that the caller is expecting. The caller is expecting all the registers to be the same as they were before. So when we entered this function right here, right before we entered this function, the EBP was up here and the ESP was down here. So when we go back to having returned, we want the same thing. We want the ESP to be down here and we want the EBP to be up here. In the function prologue, in the function prologue, we messed with all these registers. We set up our own EBP and we set up our own stack frame. We set up ESP to be down here and EBP to be up here. So what we want is first we get rid of our own stack frame because we don't need it anymore. We're done calling. So that means we move the EBP upwards, or ESP upwards. That's how we deallocate the stack. And then we know that, okay, we want to get back to the state where the EBP is up here and the ESP is down here. So what we're going to do is I know that we saved the original value of EBP on the stack. So now we're going to restore it. We're going to pop this value off the stack, which is our saved EBP, and store it back into EBP. So we're restoring the value of the EBP up here. And then when we return, we do the same thing. The EIP gets restored to where it should be after we've called the function, and the ESP moves back up by 4. So the function prologue and the function epilogue are very closely related. Basically, anything that you do in the function prologue to allocate space, to change registers, you have to undo that in the function epilogue. Does that kind of make sense? ESP moves up by 4 in both the pop instruction and the ret instruction. Both of them pop a value off the stack. So you can almost think of the ret instruction as pop EIP. You can almost think of it like that because that won't assemble in x86, but it's essentially the same thing. Mm-hmm. I'm just going through questions. I think Perrin got some of these, but we'll just go through for completeness. EVP is equivalent to the FP register in RISC-V, yes.
And the other one was asking about why there are two push instructions in caller, so the -8 and the -4. So that's because we're pushing arguments on the stack. So the caller is going to push arguments on the stack, so the callee can use them. So that's why those are there.
Yeah. So if we wanted to call them with constant values, instead we could use like push. I'll just type it in the chat. Push L $1 and push L $2. If we wanted literal values as the function arguments, but in this case, we're, the code says we're going to use the values of the local variables as the arguments, which is why we have the memory references, because that's where the local variables are stored. And then we're pushing the local variables onto the stack again. All right. There are no other questions. I'll go ahead and stop the recording.